recording. Okay, so we're going to go through for the distance students who have no idea what's going on. We've assigned different groups, some problems to work through, and now we're going to be discussing in class. And I need to find the pen that goes with the tablet. Okay, so 8-5. Yes. You guys are ready. So hop on up. Someone, you have better handwriting than I do.
So you own some more. That's true. I make no excuses for my handwriting. It's horrible. It always has been.
Yeah. 8-5 is pretty straightforward.
Okay. So give kind of a rundown of the problem and what the key points are. And
Okay. So if everyone looks at 8-5, it's just comparing the activation energies for viscous flow for high temperature and low temperature. Activation energies for viscous flow. And just compare it to the ratios mentioned in the text. And the ratios mentioned in the text is that the low temperature activation energy is about twice as high as the high temperature activation energy. So there's a curve that they give up in the text for figure 8.7. And basically we divided it roughly where like the two regions are linear for the high and low temperature regions. So around 40-ish degrees Celsius, a little lower is the high
make a
temperature.
quick sketch of the
Okay.
figure.
Just make sure not to press any of the buttons while you're drawing.
So that's what the figure somewhat like. So, there's two roughly linear-ish regions that we chose to be. That's not exact, obviously, but we chose then high and low temperature. So basically, what we did is calculate the slope, and this is. I think that's 10 to the fifth. Okay, so here, this is the high temperature regime over here. This is low. So just quickly looking at it, we kind of eyeballed and got around 2, but calculating the slopes, we kind of went through and chose two different, obviously a set of points on there. So
It's 10 to the third.
it was 10 to the third. Okay.
Yeah.
That, 10 to the third. Okay.
10,000 C.
Oh yeah. 10 to the third over.
Sorry, what's N here?
That's eta. That's the
Eta is the viscosity.
Yeah. So we went through and we chose 2 points for each spot to calculate the slope. And let's see our points. So for the high temperature, should I draw all these numbers on here, or is if everyone's kind of looking at that?
Well, you'll post like an actual solution.
Okay. Well,
right, so
the general idea is basically we calculated the slope in the high temperature regime and the slope in the low temperature regime, because the slope of this is activation energy.
Okay.
And then we compare the ratios. And in the text it says it's 2, and I think we got roughly about 2.3 as the ratio for activation energy of high temperature to low temperature. So pretty.
I think this was actually an organic class, so it should be around like an order of magnitude, but it's hard to tell from the photocopy figures.
It's hard to tell. Yeah. Okay. So just just a little background, right? So why the slope on the log plot?
Because activation energy is
It's an Arrhenius.
Yeah, it's an Arrhenius relationship.
Yeah, so it's
It's proportional to x. Yeah, so I should write that down. Q. Yeah, so it's an Arrhenius relationship. So the slope of this curve represents.
Is it minus Q over?
It's yeah.
Okay.
Let's move on to the back of the class, right? Yeah.
So the slope is proportional to activation energy. So So then you calculate the slope of the high temperature, low temperature, and find the ratios, and that's the ratio of reactivation energies.
Do you have a sense of why the curve looks like that? Why is there such a distinct, two kind of distinct linear regions?
The flow mechanism
As in the
changes.
flow by changes from
Look at the text again.
Yeah. So
yeah.
okay.
The method in which
Is it to
flows
do with the
definitely
glass
changes
transition
the high
temperature?
end.
You've got basically you're going through glass transition.
But obviously we'll put answer the numbers.
Yeah, put the
little more.
put the work with the numbers up. And,
Okay.
right. So questions from everybody else? Okay, so you guys have the cooling glass sphere. Yeah.
Oh, wonderful. I'm all good.
That's why I said that one.
My existence.
All right, so question 8.9 first asks about what the temp. I gotta get my pen straight. First asks about the temperature of a material as a function of distance into it, and I think we can all agree that's relatively trivial, and that you would get a much lower temperature on the surface if you're cooling, and eventually you get some bulk temperature, T or X. And then part B asks us to relate that to free volume versus X.
So just one second. If you wanted to be quantitative with the first part,
Yes.
right? What's the right? How would you do that?
We would look at thermal conductivity and
Yeah, there's 480 flow.
yeah.
Right. So okay. Right. Or diffusion of heat.
Yes.
So square root dt.
And asks us to relate that to free volume, which we know as things cool at a faster rate, we have far more free volume, and as things cool slower, we have less. So we figured we'd have some sort of sigmoid curve in which you have a surface free volume at a maximum, and then it would peter out to a bulk.
So that's as when it was completely cooled.
Yes.
Right.
So part C comes up with a hypothetical situation in which, actually no, there's another part of B, isn't there not? Part B has two.
Oh, Part B wants us to argue why that would result in a tensile surface stress and a
That's right.
compressive
Okay.
internal stress.
So if the surface has more free volume than the bulk, we know that the surface would basically would pull on the interior of our hypothetical cube, because the interior is going to contract more, and the exterior is going to want to. And the exterior is not going to contract as much, and since we don't have voids forming, that's going to lead to a tensile stress in the surface and a compressive stress in the bulk.
Okay, so think about it from a just thermal expansion point of view, right? So you've got a uniform ball at high temperature, right? The surface cools more rapidly than the inside, right? So eventually the surface reaches a point where it doesn't flow anymore, right? But it has been shrinking relative to the inside. So at this point, is the surface under tension, tensile stress, or compressive stress? Right? It's under tensile stress. But it can't, it's not moving anymore. Right? Now the inside cools. Right? And it contracts, and it's pulling against the surface. Right?
This gets into Part C, I think.
Oh, okay, sorry.
Yeah, there's
Yeah, that was the second part of Part B.
Yeah.
That was the second part B. Oh, I was getting part C and part B
Yeah.
confused. Okay,
Yeah,
so,
so-
sorry. I'll let you guys go ahead.
All right, building on what he said, part C assumes the same behavior, except the interior is free to have some viscous flow while the surface is fixed.
Yes.
The surface is fixed, interior can flow a bit. And what ends up happening is because the surface is fixed, and you get some relaxation, in which you no longer have compressive stress, but because you have less free volume and everything's relaxing a bit, you now have the interior is pulled to the surface. And to balance that out, the surface is actually compressed a little bit because you have some viscous relaxation and the difference in free volume between the surface and the bulk.
So you end up with a set of compressive stresses on the surface. So is it going to be easier to break or more difficult to break than?
It should be more difficult to break.
Is this how glass tempering works?
Basically. So, has everyone seen anyone make Prince Rupert drops in high school?
I've seen
What?
Prince Rupert drops?
Oh, they're awesome. No.
Oh.
Maybe I'll make some for Monday.
It'll be fun.
Wait, you're gonna make some?
Make one for Monday.
Oh.
They
Basically,
basically drop.
you just take glass, heat it up with a propane torch, so a blob of it melts into a bucket of water. So you get a tadpole-looking thing with a long, weird, squiggly tail. Then you've got huge surface. I should draw this on here. So, right. So you get your weird glass tadpole. Right, and up here is the situation that was just described. So you have very large compressive surface forces. And back here, this is thin enough that it cooled uniformly, right? So this is still very fragile and very thin. Up here, you've got a big blob, right? And you can basically take this and whap on it with a hammer, the front part, and nothing will happen, right? But think about it for those who haven't seen this. Okay, so show of hands. Who is not familiar with what a Prince Rupert drop is? Okay, so only those of you who raised your hand are allowed to answer the question. What's going to happen if I break the tail, the little bit of the tail off?
It's just gonna crack, right? It's like regular glass.
The tail's going to crack, but then what's going to happen?
It will lead us to the crack in front.
Yeah, right. I still have some surface compression out here, right? There's still a gradient,
Okay.
right? But it's not nearly as much as up here, right? So now I get a crack, right? I get cracks that propagate in, right, from this little end. What's going to happen? I've got a imbalance of forces here.
Okay. The split.
Yeah, which way is it going to run? It's going to propagate lengthwise into this region where we've got huge compressives, right? So you're throwing the crack downhill in the worst possible way, right? How fast does that crack travel?
Sound.
Basically the speed of sound, right? The shear wave velocity in the material, right? So you've got this crack that's propagating at the speed of sound
To where?
into
Into the really high.
the really high, right? So now I've got huge tensile stresses here that want to relieve themselves
Okay.
on this internal, right? This is all massively tensile. This is massively compressive, right? So this then radiates out tons and tons and tons of cracks. Once this tensile stress is relieved, this is now in a state where it's going to want to crack, right? So basically, you can do whatever you want here. There's videos online of people hanging these and shooting them with a 22, right? And then basically they deflect the lead. right? Or taking them and whacking them on a hammer.
The Cornell Glass Museum makes some really big ones that
Yeah.
are great YouTube videos of.
and if anyone watches the hydraulic press channel, this Finnish guy, yeah. So he made one, but well, anyway. So if you, I'll tell you about that in a second. But if you break the end of this, the whole thing basically instantaneously explodes into a fine powder, right? And it happens at the speed of sound. The hydraulic press channel actually recorded the first ever instance of fracturing a Prince Rupert drop from the bulb end, but they put it under a 100-ton press to get it to do it. So,
All right.
and
Is that cheating?
it didn't explode nearly as
Much.
Spectacularly.
as spectacularly as simply breaking a little bit off.
Now, it is worth noting for the big ones, it's not particularly easy to snap the tail off either.
No. But the ones I'd be making a 5-gallon bucket of water with an SVP beer bottle.
Oh,
Right? So okay, so one more. So who's next on the list? Super, I think that's you got your team. Who's gonna go? Who's gonna volunteer or be volunteered?
I don't know the formula. You just go.
So our group got problem 8.11. So it asked us to say something about the relative activation energies for viscosity in metallic and silicate glasses. So
Don't you love vague questions like that? Say something meaningful about this.
So yeah, I don't know what to write. I'll just talk because it's like really easy.
Yeah.
Yeah, we just thought that because the metallic glasses has metallic bonding and the silicate has covalent bonding. So, but in order to do the viscous flow, you have to break the molecular bonding. So basically, just compare the metallic bonding and covalent bonds. The energy between the metallic bonds and the covalent bonds. But since the covalent bond has a higher energy, so it needs a higher activation energy to flow, to do the viscous flow.
Okay. So what's the structure of the silicon oxygen bond? Right. So how's right? It's a tetrahedron. I heard it. Okay. And so that means that silicon has to be what hybridization?
SP3.
Right, so it's SP3 hybridization, right? So you get a nice, really strong, directionally, right? There's no weak directions. Right. So do you know what the bond energy roughly is?
400 kilojoules. 400.
400 kilojoules.
400 kilojoules. So, and in the metallic bond,
I think it varies with different kind of
but just
350 something.
well, how much?
350.
Be less than that, right?
It's higher.
It seems higher. Right. So think. Right. So take a look at that, right? See what some of the atomistic people. Right. So, but think about it. There's probably a unit disparity there. It should be.
order of magnitude.
I don't know if it's quite an order. It's not an order of magnitude, but it's more than
Double
it's
or
more than 20%, right?
Substantially more.
Yeah. So it should be. Right.
Iron bonds are 75 plus or minus 17 kilojoules per mole. So we're looking at 75 versus 400.
75 versus 400. So you're a factor of
At least a factor of 4.
3 to 4. Right. Right. It's going to be slightly weaker if you're in the transition metals, right? Because there's pesky d orbitals getting away. So
But in metallic classes, there will be different metallic elements.
yeah.
Those
So
bond energies.
it's an alloy, right? But we're talking roughly here, right? Order of. Right. So between 1 and 10 versus between 1/10 and 1, right? Right. Is the right, so the order of magnitude kind of difference, right? And so that explains, right, a couple important things, right? So why soda lime glass is so much easier to work than pure silicate glass,
Oh,
right? Right, because the sodium basically disrupts the tetrahedron, right? So you have it doesn't actually bond; it sits in the rings, right, and causes the failure of the tetrahedron to close. Right, so now you've got free ends because you need to maintain charge balance, right? So you're sticking ionic things in a covalent web, right? And so you now have ends that you can move much more easily. Also, why quartz is much more difficult to form, like by glass blowing, right? Because you have such a very narrow working window where your viscosity is low enough to actually, right? Because it's sort of lime glass, you've got a wider range of temperatures that you can flow over, right? Because you've got this, but when you've got a nice, perfect covalent network, right? You have a small temperature between when you can easily break those bonds and when it melts, right? So it takes a very skilled person, right? That's why chemistry departments used to all have their own glass blower on staff.
Don't we still have one?
I don't know. We have one? Okay. But, you know, the people who do scientific glassware are really great because they can do quartz. Right? So, okay, so we'll stop there. Everybody post their answers over this weekend, and on Monday we'll go through the rest of the groups and go through a couple key, some of the, what I felt are key concepts from the lectures.
So is this due next Monday? Or?
Well, I'll post the homework assignment will be due Wednesday.
Okay.
Right, but the other groups, right, everyone posts the solution to their group's problem over the weekend. On Monday, the remaining groups will discuss. And I'll also hit a few key high points from the lecture.
I can do that.